Let's make it concrete with an example that I first give us a schematic and then analyze using LT Spice. So say we have a 1 volt peak cosine waveform, and we can represent it as this with variable omegas, or if we prefer to write it in terms of frequencies in hertz, we can write it like this. Same thing either way. And notice it's 1 volt. So its phasor equivalent will always look just like 1 at an angle of 0 degrees. And we're going to make a voltage divider out of this. Here's a 1 kilo ohm resistor up here, and it's going to be in series with a 160 nanofarad capacitor. And we're interested in reading what the voltage is across that capacitor. So first realize that up here, we're in the time domain. We're talking about the capacitor being a 160 nanofarad capacitor, not a generalized frequency dependent impedance. And we're using lowercase outputs as a function of time and voltage sources that are a function of time for the input. Now, what we want to do is see how this output changes versus frequency. So we'd like to plot that peak voltage, which is a number, even though this waveform, of course, looks like this coming out of it. We're interested in plotting what that peak voltage is, VP, versus not time now, but versus frequency. So as we increase frequency, how does that change? And let's take a limiting argument. When the frequency is 0, this cosine of omega t just becomes 1 volt. It's a 1 volt DC source. This capacitor at DC looks like an open. And so we know we're going to start out at 1 volt for low frequencies. As the frequency gets infinitely high, we know capacitors look like shorts. So then this voltage output will be across a short. All the voltage will be dropped across the resistor. None will be dropped across the equivalent short. We know for really high frequencies, we'll be operating here. So we expect to see something that looks like this. Now, you could analyze it over and over using phasors. For every single frequency, you'd have to replace this with the impedance at that frequency. You know what that would be? It'd be 1 over j omega c. If you wanted to measure this in frequency in hertz, the omega would be 2 pi f. And you'd have to analyze this for low frequencies, higher frequencies, all the way up, and you'd get a curve like this. This is what LT Spice will do for you automatically. Let me power up LT Spice and show you. So we're going to build a schematic in LT Spice. To do that, we will start off clicking this, our new schematic button. By the way, if you want to install LT Spice, it is free. Just do a search for it. It's part of analog electronics now. It's called LT Spice because it used to be made by Linear Technologies, which got bought by Analog Devices. So at first, we need to put down our voltage source. This component that looks like an AND gate has all of our possible voltage sources, all of our possible components in it. We can move over to our voltage source and place that. Hit the escape button to get out of place mode. We need a resistor. You can find that under components too, but people use resistors so often that there's a built-in resistor symbol up here. You can hit Control R to rotate these resistors around. Escape gets out of that mode. We'll use a capacitor next. Escape. And you always need one ground, at least one ground. So here's our ground. Let's wire it up. The picture of the pencil is a wire. So here's our first. Notice that when you correctly connect a wire, oops, hit escape to get out of that. Notice that when you correctly connect a wire, the dot, that open circle goes away. Now we have to connect our ground. And whenever you successfully connect two wires together, it forms a rather large and obnoxious closed square. Now I'm going to define, whoops, I scrolled right away. Let's get out of the wire placing mode. And this button up here, zoom to full extents, will bring us back to where we should be. All right, now we're going to define what our components are. The easy ones are the resistors. So you right-click the symbol. Don't right-click the value. That will just change the text that's shown. It won't actually change the value. Click the symbol, right-click the symbol, and we said this was going to be 10K. LT Spice understands Ks and nanos and whatnot. Right-click the symbol again, and we'll choose 160 nanofarads. The farads part is optional. I could have just as well said 160 nanos, and it would know it's farads because it's a capacitor. And then we'll right-click our source. Now, it's definitely not a DC value. This is an AC source that we want to have vary with frequency. So we'll click Advanced. You might think you want a sine, but you don't. A sine is a source that starts out at 0 and then suddenly starts to oscillate. So we'll have all sorts of odd transients. We don't want that. Instead, it's not going to be a function. It's going to be over here, small signal AC analysis. We want to say it's going to be a voltage peak of 1 volt. We can keep the phase at its default 0. And notice you don't specify what the frequency is. Unlike with sine, you do specify what the frequency is. You don't specify the frequency for small signal AC analysis because we're going to be sweeping it to a bunch of different frequencies. All right, now we can specify where our output is. You could just click on it, or if you want to have a nicely labeled graph, you can choose a net label, and we'll call it V out, and just click out the point you want to label it. So now, instead of having to click on here to say we want to graph this voltage relative to ground, we can just say we want to graph V out. All right, let's set up the simulation command. That's edit simulation command down here. And we have all these different types of simulations. Transient means it will create an oscilloscope-like graph that shows voltage versus time. We don't want to do that. We want voltage versus frequency. That's our AC analysis. So what type of sweep? Decade means that you'll specify the frequencies at which it sweeps in decades. So 100, 1,000, 10,000. And let's start it off at 10 hertz, and let's finish it up at what's going on at 100 kilohertz. So again, LT Spice understands what a K is. Much easier typing a K than 1, 0, 0, 0, 0, 0. Hope you got the right number of zeros. And then number points per decade. This harkens back to when I was an undergraduate, and computation on these things might take an hour. Now it takes fractions of a second. So we can easily say, plot 100 or more points per decade. So between 10 hertz and 100 hertz, plot essentially 100 of these phasor analyses, and then do the same between 100 hertz and 1,000 hertz. And computation is cheap now. So here's our command to do all that plotting. And now we can run. Of course, it does it instantly thanks to modern computers. And we'll click that V out node. And this shows what's going on at our V out node. So let's analyze this. What this is saying is that if we put in a 10 hertz, a 1 volt we specified, a 1 volt cosine at 10 hertz with no phase offset, what we're going to get out is going to be a 0 dB. All right, so this is something that we haven't talked about. We'll talk about what dB is next semester in signals and systems. To get rid of that, right-click that axis, choose linear, and then it will have a more familiar types of units. So if you put in a 1 volt, 10 hertz, 0 degree cosine wave, what you'll get out will be this solid waveform in magnitude and this dotted waveform in degrees in phase offset that you can measure on the right. So put a 10 hertz, 1 volt input, and you'll get a 1 volt, 10 hertz at, bring the dotted line over at just less than 0 degrees offset. So maybe it's going to be, you put in a 1 volt cosine, 10 times 2 times pi times t plus 0 degrees, you get out a 1 volt times cosine of 10 times 2 times pi times t minus maybe 6 degrees. And if you put in a 100 kilohertz waveform. So you put in a 1 volt times 10 kilohertz at 0 degrees, you'll get out a almost nothing, a 0.005 maybe cosine of 10 kilohertz at about minus 90 degrees, minus 96 degrees. It's about minus 90 degrees, trust me. So we're often less concerned about the phase here and more concerned about the magnitude. So I'm going to make it easy. I'm going to right click the phase side on the right and choose don't plot phase. And now we're just looking at the magnitudes. And this really encapsulates what this circuit does. It passes low frequencies. When you put in 1 volt in at frequencies from 1 to maybe 30 hertz, it pretty much passes it. And then at around 100 hertz, it starts, you can see it starts to cut it off. It maybe it only allows 0.7 volts peak to pass. And then for frequencies greater than 10 kilohertz, it really cuts it down to pretty much 0. So this is an example of a low pass filter.